Okay, last time we talked about VO2 and VCO2. We're going to talk in part of this lecture about how we can use those values here. So we're going to talk about something called the respiratory exchange ratio. So here are the outcomes for today. So we've got something called RQ, which is the respiratory quotient, and basically what it is it's the ratio of carbon dioxide production to oxygen utilization, but at the cellular level. Okay, but in order to actually accurately measure this, we need to do measurements in arterial and venous blood to measure the blood gases. Venous blood's really easy to do. It's been a little while, but I can do it. Arterial blood, on the other hand, you need a physician, and I am a doctor, I am not a physician, so I can't do that. And there's just all sorts of issues or potential complications when we're messing around with arterial blood draws. So we don't really measure RQ very often, but we can measure RER relatively simply, especially if you've got the equipment, which we do. So RER is the ratio of VCO2 to VO2, but this time it's at the mouth. So we want to know, based on the gases that we're inspiring and expiring, what's the ratio of CO2 to oxygen? And so this is the most common way that we estimate RQ. So this is an indirect method. All right. Now, you have to understand that with RER, this is a good estimate. Remember, it's an estimate. It's not the exact. Under what we call steady state conditions and submaximal exercise. So steady state is where you're doing something at a specific workload and you've given your body time to adjust. And so you're kind of in this homeostatic state. So lots of things are changing, but like your heart rate will be consistent. The amount of oxygen you're using is consistent, that sort of thing. All right. And so with this RER, we can actually estimate the fuels that we're using. Okay. So, and when I say fuels, I'm talking about what percentage of fuel is carbs, what percentage of fuel that we're using is fats. So with RER, if we're using 100% fats, we'll get a value of 0.70. If we're using 100% carbs, we'll get a value of 1.00. One of the things that's important to know about RER is that it doesn't take into account proteins. Okay, and that's not that big of a deal because we don't use that much protein directly for energy. All right, now it is possible that our RER can drop below 0.70, and that's when we're producing glucose, like it says here, from fats and proteins. And we can all, I was getting ahead of myself. So typically during rest, though, we're between 0.78 and 0.80. So it's mostly fats with a little bit of carbs sprinkled in there. Maximal exercise, we get up to 1.00, and we can in fact exceed 1.00, but this is something we'll talk about later on. Okay, but generally we're between 0.7 and 1.0. So what determines this? Well, what are you using for fuel? Okay, so the substrates, and specifically fats and carbs. Okay, now if we take both fats and carbs and we create a chemical equation that shows how we produce ATP, we get something like this. So for a single free fatty acid, we're going to utilize 23 oxygens, but we're going to produce 16 CO2. And so we take the ratio 16 CO2 divided by 23 oxygens, and that gives us a ratio of 0.70. So if we're only using fats, that's what we would expect our RER to be. Similarly, if we're only using glucose or carbs, notice that the equation's different. Okay, and so we use 6 oxygens, but we produce 6 CO2s, and so 6 divided by 6 equals 1.00. Okay, so ultimately what happens is that these values come from balanced chemical equations. This comes from something called stoichiometry, which is a part of chemistry that involves using relationships between reactants, so the stuff on the left side of the equation, and the products to determine whatever it is you're looking at, so we can determine what fuels are being used here. Now, in order to do this, we have to have this big old complicated table. It's actually not that complicated, but we'll need to use this to estimate how many calories we're using. So we can do this based on the amount of oxygen that we're consuming. And notice that for every RQ or RER, we have a different amount of oxygen that we're using. Now, remember we talked about we use fats at low intensities, we use carb at high intensities. Well, notice here that if I'm using only carbs, I'm getting 5 calories of energy per liter of oxygen, whereas when I'm only using fats, I'm only getting just under 4.7 calories per liter of oxygen. And yes, this says kilocalories. That actually means 1,000 calories, but when we talk about calories in our daily life, we're actually talking about kilocalories. Okay, so the amount of oxygen or the amount of calories we're getting from a liter of oxygen determines on what the mixture of fuel sources is, right? And so if you see here, we've got the percentage of carbs, and over here we've got the percentage of fats. And so these should always add up to 100. And so just depending on what's going on will give us an idea. Okay, so we don't take into account protein because it's essentially insignificant. And so this RER gives us that idea of what percentage, right? So if my RER is 0.9, I'm using 67% carbs, 33% fats. Okay, so when it comes to calculating this, it's determined the rate of energy production or energy utilization is determined by the work that you are doing. And so we use that indirect calorimetry, so VO2, VCO2, RER, to estimate this. And we can use this, but only if a couple of conditions are met. So if we want to really accurately determine how many calories we're using, that sort of thing, we need to be at steady state, okay, so where everything's constant, so you're at like a constant intensity and you've been there for a while, and this needs to be during submaximal exercise. Maximal exercise kind of changes everything because we end up getting an RER above 1, and we'll talk about why that occurs later on, but just not in this lecture. Okay, so assuming that that's the case, if we're at steady state, we're at submaximal exercise, and we have these 4 pieces of information, we can calculate how much energy we're using. Okay, so we need to know VO2, our RER, we need to have access to this table, and then we need to know how long we were exercising for. So for example, let's say that your VO2 is 2.3 liters of oxygen per minute. Okay. Let's say that your RER is 0.83, and so we go to 0.83, and that's right here, and so we know that right here is 0.83, so we know that we're using 4.83, or we're burning 4.83 kilocalories per liter of oxygen. Okay, so you're going for 60 minutes. You exercise for 60 minutes, constant, steady state exercise, and so we go 2.3 times 4.838 times 60. And I wish I had, but I hadn't just because it gets a little messy, a little crowded. I know that Trevor and the lab GAs would want you to do this. Use your units. So this should say 2.3 liters per minute times 4.838 kilocalories per liter of oxygen times 60 minutes. And then everything cancels out. And what we find out is that we burned 668 kilocalories during this activity. All right. And so the next question is, well, how much is coming from fats? How much is coming from carbs? And we go back to this 0.83 RER, and we know that 43.8% of our energy was coming from carbs, and the remaining 56.2 was coming from fats. And that's that. So can you define RQ and RER? Can you explain the conditions where it's okay to use RER to estimate fuel consumption? And how is it possible to have an RER below 0.7 or above 1.0?